to thank to WILFREDO for inviting me to participate in this very nice meeting. Well, I talk about an Arrow-Debreu condition in the setting of generalized concavity. The outline consists in an introduction. I describe the Arrow-Debreu condition. And this Arrow-Debreu condition was a motivation for other generalized concavity notions. I talk about them. And also, these generalized concavity notions generate some confusions. And we talk about these generalized confusions. And in order to put order or increase the confusion, we define Arrow-Debreu functions. I talk about the properties of these Arrow-Debreu functions, characterization of Arrow-Debreu functions. We talk about the separation property when we have a consumer problem. The consumer problem is to maximize a function called utility over to restriction set called budget set. When the price is constant, we can reduce this consumer problem and maximize an utility function over a semi-space. And we try to introduce some separation properties in this case. And finally, we give other one results. Okay, quasi-concavity is very important in some branches of science, as for example, in economic theory, optimization theory, gain theory, decision theory. This importance was pointed out by Mordecai Abriel in 2010, by Juan Enrique Martinez Legaz in 2005, and Jean-Pierre Crouzet in 2003. We remember that quasi-concavity was introduced by Bruno De Finetti in 1949. And this notion of quasi-concavity was the first generalized concavity notion. The second one appears in a pioneer, how to point now? Here. In the pioneer of general equilibrium model introduced by Arrow-Debreu in 1954. This condition was imposed on utility function which represent the consumer preference. This condition, Arrow-Debreu, states that the utility of a strictly convex combination of two choices with different utility is always strictly greater than the choice with lower utility. This is natural in economics theory. Well, this condition, called from now as Arrow-Debreu condition, by itself, it is well known that has nothing to do with quasi-concavity. Okay, sorry, the technical trouble. Okay, where are you there? This Arrow-Debreu condition was motivation for some generalized concavity. For example, the semi-strictly quasi-concavity. This notion appears in the PhD thesis of Elkin in 1968, and a paper of Ginsberg in 1973. Other notion inspired in the Arrow-Debreu condition was strictly quasi-concavity. This notion appears again in the PhD thesis of Elkin in 1968, in the paper of Ortega-Reinbold in 1970, and again in the paper of Ginsberg in 1973. Only for remember the notion of quasi-concavity is this. The confusion. the first confusion appears when some people try to define strictly quasi-concavity as an equivalent to semi-strictly quasi-concavity, when semi-strictly quasi-concavity has nothing to do with concavity, quasi-concavity. Okay, all right, I wait to resolve this problem, this technical problem. Okay, the second confusion was given by Gabriel in 1976 when he tried to define the strictly quasi-concavity, strongly quasi-concavity using the strictly quasi-concavity. This is in the part of mathematical people. For economics people, the confusion was generalized because the first was hard, the second was a lot, the economical people who work in equilibrium theory, they prefer, instead to Arrow-Debreu condition, he preferred to the strictly quasi-concavity. But Arrow-Debreu condition has nothing to do with quasi-concavity. Okay? And people, for example, Hart in 1979, Dana and all in 1999, Allows Liban in 2008, Martin da Rocha and Montero in 2009, among others. No? Okay. Now I make some remarks about this Arrow-Debreu condition. This notion, semi-strictly quasi-concavity, is exactly Arrow-Debreu condition. The second, in equilibrium theory and economy, this condition Arrow-Debreu coming with other assumption. For example, in a paper of Arrow-Debreu is coming with continuity. And Arrow-Debreu proved that Arrow-Debreu condition plus continuity implied quasi-concavity. After, in 1967, Karamarian said, you don't need continuity, only with upper semi-continuity, you obtain the same. Okay? Another remark is that strictly quasi-concavity implied quasi-concavity. Okay? So, in order to put order, as we said, or increase the confusion, we define Arrow-Debreu functions. We said that a function is Arrow-Debreu function if this condition holds. This is exactly the Arrow-Debreu condition. Okay? The first bad news is that this function, the effective domain of the function, is not necessarily convex. A sample example is this. Since the effective domain is not necessarily convex, the function is not quasi-convex. Here we have an example of function where the quasi-concavity is destroyed in only one point. Only one point destroyed the quasi-concavity. Okay? This function satisfies the condition of Arrow-Debreu, but it's not quasi-concave. Properties respect to Arrow-Debreu functions. Here we use this notation. This notation is for the upper level set and level lambda. This is the notation for the strictly upper level set as level lambda. This is the notation for the imaging of the function u. The first property coming from the definition of the Arrow-Debreu condition. This other one is very important because I try to get answer what happened with the point who destroyed the quasi-concavity. If we have this case, this is the point who destroyed the quasi-concavity. Of course, is the convex combination of other one in the domain. We have that this closed interval minus this point is included in the upper level set. This is very important because we have the following theorem. If we have an Arrow-Debreu function, the closure of the upper level set is convex when lambda, the level lambda, is the imaging of the function u. And a strictly upper level set and level lambda is not empty. Moreover, we have this other very nice property. Because when we work with concavity function, the literature said out that there exists some tool will replace the gradient or the derivative. In general, when the quasi-concavity, the concavity is relaxed, we have some other notion called generalized concavity. It's not possible. For example, for pseudo-concavity, we talk about a few minutes, it's not possible to work with the normal cone of the epigraph because the epigraph is not convex. But we lost one dimension and we work in the level set. In the level set, it's possible to construct a normal cone. But for quasi-concave function, it's not possible to do that. So this condition is very important in order to introduce element as a subgradient, for example. Pseudo-concavity. Pseudo-concavity was introduced because in optimization theory, in order to maximize concave function, we have two interesting properties. The first one is the local maximum is a global maximum. I think the fifth speaker about this. The second nice property is the necessarily condition implies sufficient condition. This notion of pseudo-concavity try to increase the family of concave function, maintain or mind these two very nice properties. But unfortunately, from the point of view of mathematics, the concavity was defined in a vectorial structure. So any other generalized concavity notion need to live in the same vectorial structure. Don't need topological structure. So, of course, the work, the importance of this is very important in optimization theory. But we are working in a more general theory is mathematics. From the mathematical point of view, I think that it's not a good idea to call it to this notion as pseudo-concavity and consider it as a generalized concavity. This is the reason because there exist many notions in order to define pseudo-concavity with the topology. Here we consider 4 of them. The first one was introduced by Ortega and Raybould in 1970. The condition is this. Here, in this condition, the author don't need topological argument. From now, we call it all the functions satisfying this property as all-air function. The second one was introduced by Conlonsi in 1983. Unfortunately, he used upper right in the derivative, but he tried to debilitate to because it is more easy try to understand as a limit, okay? But this is other one that we consider here. The third one was introduced by using XI and Sosa in 2009. And the condition is this. In this condition, don't use topological argument. And I think, from my point of view, particular from from point of view. This is interesting because convexity, of course, I work to concavity, but it's better to see it in convexity. The algebraic here of course, x is dx plus 1 minus ty. Yes? This is convexity. This equation is equivalent to this one. On the other side, for monotonicity, we have that an operator is monotone. And it is equivalent to say that okay? When pseudo-monotonicity appears, said if this is greater or equal to 0, then it implies that this is less or equal to 0. I think that it's natural to consider the pseudo-convexity if this is greater or equal to 0, imply that this other part is less or equal to 0, following the analogy respect to monotonicity. Okay? The difference between convexity and concavity is only the sign. Okay? So, this here is for convexity, for concavity, for pseudo-concavity, this is equivalent to this. So I think this notion is better following the analogy of pseudo-monotonicity. The fourth definition was introduced by Jean-Pierre Crouzet, my great friend, in 2010. And here we consider this condition. And here we use the interior of the upper level set, a level UX, and here he used the closure. This condition implies that the upper level set and the strict level set compare the same closure. It is the property obtained from Arrow-Debreu functions. And he introduced the notation because he was interested in introduce a subdifferential for this class of functions satisfying this property. Relation between all the functions defined before. We have that our function implies that this function is Arrow-Debreu function. Our function implies Coulomb-Lonzi function. If the function u is strictly quasi-concave, if u is strictly quasi-concave, then u is IKS function. If u is quasi-concave function, then Coulomb-Lonzi function implies IKS function. If u is quasi-concave function and the interior of the upper level set, a level lambda, is non-empty for any lambda strictly less to the supremum, then Arrow-Debreu function implies Crouzet function. IKS function implies Arrow-Debreu function. And so on, we continue time any relation between all that functions. Well, now we introduce some characterization of Arrow-Debreu functions. But before we need this definition. This definition appears in Ali Prantian Border in 1999. And it's in order to introduce other classes of functions called upper closed function. The difference between upper closed function between upper semi-continuous function is this. The level set is only belong in the imagine of the function. So if the function is upper semi-continuous, then it implies that the function is upper closed, but the converse is not true. So the first characterization is if the function is upper closed, then Arrow-Debreu function is nothing else than the using XI SOSA function. The definition is coincide in this class of functions. The other is, okay, I said, no, don't use a topological argument. Okay, I don't use a topological argument. If the function U is quasi-concave, again, Arrow-Debreu function is equivalent to using XI SOSA function. This reinforces this idea that this is natural for pseudo-convexity. Okay, now we talk about the separation properties. As we said, for the consumer problem, the consumer problem consists in maximize an utility function subject to okay, and this is a semi-space generated by this hyperplane. Okay, and we try to introduce a separation property in order to separate this restriction set respect to some other set. Okay? The separation is the following, because we try to separate the semi-space, the separation whole when the set is included in the other semi-space. This is equivalent to the particular separation of two sets. It's not a new definition, it's the classical, but it's a particular case. The first sufficient condition for separation is if the function is an Arrow-Debreu function, and this condition holds, if X is the solution of this problem, the consumer problem, then this hyperplane, this hyperplane, separate the budget set respect to the upper level set and level UX. In economics, this is called to the preferred set. Preferred set respect to this point. This point is called the individual demand of the consumer. The necessary condition is the following. If we have this condition implies this other one. It's easy to see there. We have the hyperplane separate the budget set respect to the preferred set a level UX, then X is a solution of the consumer problem. Okay? So for this class of function, Arrow-Debreu function, which has nothing to do with quasi-concavity, it is possible to obtain some interesting properties. And from the view of the optimization theory, this is important too. Other result is the following. Here we consider U as an Arrow-Debreu function. This is nothing else than the recession set of this upper level set. Recession set of Professor Nicolas Hadjisabat talk in the I think what's on the first day of the meeting. This is the dual comp of the set K. Lambda is the supremum, not necessarily is real, it can be equal to plus infinite. And we define this operator, C. C is nothing else that if we change the price, if we are thinking in the consumer problem, if we change the price, this is the individual demand. is the operator in order to obtain the solution of the consumer problem for each price. It is well known that if the function is Arrow-Debreu function, each upper closest this has nothing to do that. Each upper closest function attains or obtains his maximizers over compact set. You can see the result in Ali Prentice and Border in 1999. So the result is the following. If we have an Arrow-Debreu function, lambda don't belong in the imagine of the function u, then the graph of this individual demand, the operator of the individual demand, is closed. We don't need any other assumption respect to utility function. We need only that this function is Arrow-Debreu function. We need other one. Of course, yes, is upper closed too. If the utility function is upper closed and Arrow-Debreu function, the individual demand for the consumer problem is closed. This is very important in economy, because in economy, the people is trying to find an equilibrium of the market. Yeah. Okay, that's all for. Thanks. Questions?